This is a 20-sided die. And if I try to balance it on one of its corners, can't do that. It won't bounce. But if I spin it, I can get it to bounce, to stay up on one of its corners. This is basically a spinning top, if you're familiar with that toy. And it'll stay up until it stops, or I shouldn't say stop spinning, but starts spinning slowly enough that it'll end up toppling over. Now, I can do it with a 20-sided die, but I can also do it with a 6-sided die. Same thing, I can't balance this on a corner, but if I very carefully get this spinning, oops, spun right off, but I can get it spinning on one of its corners. There we go. And the question is, why should spinning matter? Why should that matter in terms of it being able to stay up, to be able to balance on one of its corners? It has to do with a quantity we refer to as angular momentum, which we represent with a capital L. Okay, this is angular momentum. And just like regular momentum, angular momentum must be conserved. The total amount of angular momentum in a closed system remains constant. And just like regular momentum, angular momentum is a vector. So direction matters. And that means the direction has, for the whole system, for the total angular momentum for the system, the direction won't change. So let's do just a simple example. Let's say we have two objects. We'll say object A and object B. Okay. And at the first moment in time, let's make a little chart here. So my initial moment in time and my final moment in time, we'll say that A here, object A, has an angular momentum of 10. And I'll say that's 10 up. And I'll say that B has an angular momentum of 5 down. Now, if sometime later, A, I look at it and it has an angular momentum of, let's say this is 8 up. Well, the total amount of momentum can't change, and so I can use this knowledge to figure out how much angular momentum B has. Now here, if you look at this, the total, this is 10 up, this is 5 down, so we'll call it down negative. That's going to be 10 minus 5. That means there's a total of 5 up. Which means here, if there's 8 up, okay, and I need, the total amount can't change, so I still have to have 5 up for the whole system. So, of course, that means then I have to have 3 down, because 8 minus 3 is 5. Okay. The total angular momentum has to remain constant. And that's what I've done. I have a closed system where I only have two objects, A and B. So the total angular momentum has to remain constant. In this case, it has to always be 5 up. Now, one thing I haven't talked about is how do we calculate angular momentum? The formula is L equals I omega. Omega is just the angular velocity. I is known as the moment of inertia. The moment of inertia tells us essentially how difficult it is to change an object's, well, ultimately it's angular momentum, although you might say it's state of rotation. The smaller the moment of inertia it is, the smaller the moment of inertia is, the easier it is to change the object's angular momentum. But the bigger the moment of inertia is, the harder it is to change. The moment, if you're trying to actually calculate the moment of inertia, the value depends on how the matter is distributed about the rotational axis. So if I'm looking at this toy, this propeller, it's spinning here, so how is the matter distributed about the rotational axis? And I would go through and calculate that to figure it out. Or we could talk about the 20-sided die when it's spinning, how the matter is distributed about the rotational axis, or even the 6-sided die when it's rotating. Now, we're going to be looking at some very specific shapes like hollow spheres, hollow cylinders, and solid cylinders. And these shapes have specific formulas for calculating the moment of inertia. So, for example, if I'm talking about a solid cylinder, so if I've got a solid cylinder, that formula is 1/2 mr squared. This is the formula for the moment of inertia of a solid cylinder, 1/2 times its mass times the square of its radius. This formula is in the content section, as are the formulas for the other shapes. The last thing I want to mention here with regards to moment of inertia is are the units. Moment of inertia, not moment of inertia, the angular momentum. The thing I wanted to say about the angular momentum are the units. The units for angular momentum are joule seconds. But we could talk about moment of inertia units, since I was saying that's pretty straightforward. These would be kilogram square meters. Those are the units there. But yeah, for angular momentum, it's joule seconds. You might remember that regular momentum, its units are Newton seconds. So there's a similarity there. No surprise, since they have similar names.